Yay. All right. So this is your homework. So your homework assignment is to convert this particular Boolean expression into a CNF, into a conjunctive normal form. So that means the first thing we need to know is what is a conjunctive normal form, and what can we use, what tools do we use to convert something like this into a conjunctive normal form. All right, so let's go ahead and go back to the notes because everything actually comes from the notes here. The notes actually has a kind of obscure way to describe what is a conjunctive normal form, but it is still a description, and I have no idea why it's not converting some of these into actual equations. We'll give it a refresh, and it is still not doing it.
Hmm.
That is really odd. Or maybe it's just taking its time to do it. I did make some changes to the notes, so maybe that's why. Ugh. Ugh. It's not doing it. I don't like it. This is not good. Okay, one more time. Okay. You guys saw that, right? I just refreshed and go like, yeah, maybe we'll do it this time. All right, so CNF. CNF conjunctive normal form. That is a topic, after, or right at the same time when we talk about resolution. So the result is this, okay? The result is we only want to have a single rule in zeta. That's the whole point. Okay, so you don't have to choose. And it is in the form of this. If you see a disjunction like this, and you see another disjunction like this, the only thing we are really looking for is one has a psi of some kind of expression, the other one has the exact negation of that inside the disjunction. So we don't really even have to take into consideration commutative law. So we just say, okay, the commutative law is not even important. We just naturally look at the expression here and go like we can switch between the left hand side and the right hand side. But the bottom line is if you can find expression like this, and you can find another expression like this, then we can quote unquote cancel out the psi versus the not psi so that the only thing that we produce is going to be phi, which is coming from this disjunction, or rho, which is coming from this disjunction over here. Are we good so far? Okay, so this is the same thing as resolution because we need to find both of these to be true to begin with in order to apply this particular rule. Are we doing okay so far? So I hope this is relating back to what we talked about on Monday, because what we talked about on Monday is how do we apply the rules from Zeta. And this is going to be the only rule in Zeta, okay, making things quite a bit simpler. But in order to do this, we also have to make some changes to the propositional calculus system as a whole. So we use omega 1 to mean, okay, what operators only has one single um, operand, and that's just the negation operator. Okay, this is nothing new. Okay, and but omega 2 is new because omega 2 used to have a bunch of stuff, which is disjunction, conjunction, implication, and stuff like that. This time we only have disjunction. We don't even have conjunction anymore. Okay, are we still good so far? Okay, so alpha is still the same as before. We have 0, 1 as constants, p, q, r, s, t as variables, and then in this case we have phi, psi, and rho as the Greek letters, also known as schematics. So that part has not changed. So now we also have something like this. This is what we call a predicate. So a predicate in this case is a disjunctive element. That's what it's basically just a short form of is a disjunctive element, which is also explained here. So this is explaining, what can be. So it's explaining every element in alpha is automatically a disjunctive element, which basically means it can be in a disjunction. Are we good so far? It qualifies everything in alpha to say that yes, it can be an element inside a disjunction or basically an or expression. Yes, so now we have restrictions of what can and cannot be in the disjunction. So the second line, okay, let me move the mouse pointer. So this one is basically saying if you see something in alpha and you take the negation of that, that's okay too. So, but it has to be a negation of something directly from alpha. Okay. So the negation of something directly from alpha, yeah, we'll take that also as a potential element in a disjunction. Are we good doing okay so far? So if we have P, Q, R, S, T as the variables in alpha, then P can be in the disjunction, not Q can be in the disjunction, not R can be in the disjunction, T can be in the disjunction, and so on. Are we good so far with that? Okay, all right. So the last one is probably the most difficult one. So is a WFF is really just saying is a well-formed formula. So now we are defining what is well-formed with a little twist compared to before. So basically, I would end up with a bunch of expressions or a bunch of disjunctions. So the disjunctions are, mm, let me think about this. Right. Okay. So not disjunctions. So we have a bunch of phi of I, and each one is a disjunctive element. Okay. So we just have a bunch of these. Okay. We have n of those things. If I can get a bunch of um, expressions, each one being a disjunctive element, then I can make a disjunction out of those things. And the disjunction of all of these things that can appear in the disjunction, that disjunction is well formed. Okay, so let's take a step back and see if we have any questions about that. It's probably better if I can just give you an example. Okay, so let's go ahead and take a look at an example. And we are going to use Joplin for that. I really like to use Joplin for stuff like that. Okay. That's a good question because I configured that a long time ago. Um, okay. So it has several modes in terms of how you can do all your editing. I think that's, this is how you toggle the editors. So you can use, I think this one is more WYSIWYG, based on HTML. And nope, that's the only one. I don't know how you can do that configuration. I think there's a WYSIWYG mode using just the HTML editor, and then the one that I'm using is VI. Yep. All right. So let's go ahead and take a look at, we'll just assume that alpha has 0, 1, P, Q, R, S, T. And then the Greek letters really do not matter because the Greek letter should only appear in the rules in Zeta. It should never really appear as a well-formed formula. But I just want to be complete. So we have rho, we have phi, and then we also have psi. Those are my favorite ones. Okay, and you can choose different ones if you want to. All right, so assuming this is alpha, so now we can confirm a few things. Okay, so let me ask you whether this is true or not. Is a disjunctive element, and I'm just going to say, let's pick the negation, oops, neg of R. Okay, so can someone tell me whether this is true or not? And I'm going to choose a different font too. So math, I think it is RF, okay, RM, Roman. There we go. It just looks better this way. Okay, so now the question is this true or not? Well, is R one of the elements of alpha? Yes. And we only have a negation of R. So according to the rules that we talked about earlier, Is this statement true? Is this um, predicate true? Okay. Um, yeah, that one is always fixed. When we talk, yeah, yep. So let's try something else. Okay, so we'll try something else. We'll just pick, the non-negative version of t. Okay, that seems to be true too because t itself is an element of alpha. So t all by itself is also automatically going to be um, a disjunctive element. It can be something inside a disjunction. Is that okay? So now the next question is um, we are now looking at is a well-formed formula. Okay, and the well-formed formula is using the negation of r or the or t by itself. So now the question is that true or false? It is true, right? Because everything inside the disjunction is a disjunctive element as qualified by the previous two statements. So when I take not R, which is a disjunctive element, and I take T, which is also a disjunctive element, and I make a disjunction out of those two, the resulting disjunction itself is considered well formed. Are we doing okay so far with that? Okay, so this is true. Okay, so we'll mark it as true. All right. So now we have to look at some counter examples of things that cannot be the case. So we'll start with something that cannot be a disjunctive element. So what cannot be a disjunctive element is okay, this is easy, okay? So I'm just adding this one here is a disjunctive element, and then the expression that I'm evaluating is S or T. Now that would the answer to that question would be false. Are we okay with this one? Okay, because it's easy to see the ones that are positive, but now we also have to take a look at so what is not a disjunctive element? S or T is not. Why? Because S or T as an expression is neither something in alpha nor the negation of something in alpha. It involves the operator of or. So are we doing okay so far? Yes. T, T is true, F is false. Say again? S is in alpha, yes, because it is not the negation of something in alpha, nor is it the non-negative version of something in alpha. Hmm? There are only two things. There are only two things that can be in a disjunction. It is either something directly from alpha or the negation of something directly from alpha. And what we have here, okay, so if I were to show Joplin and the rule at the same time, okay, so we can barely do that, okay, which is okay. So when you look at this one here, which is S or T, is as the whole thing, okay, you look at the whole thing. Is the expressions S or T something directly from alpha? No. Is it the negation of something directly from alpha? No. So that means it is not a legitimate disjunctive element. Okay? So that also, leads to the question or the answer of this. Okay, so if I, were to put something like this, and then I'm gonna say or, okay, but this time I put a negation on top of another disjunction, which can be S, and then we'll have a or P, Q. Okay, P or S. Okay, there we go. There we go. So now the answer is false. This is not well formed anymore because when you look at the overall disjunction, okay, this this or is fine, okay, because on the right hand side we have not R and that is a disjunctive element. On the right hand side is a T. It's okay. You look at this OR here, we have a problem because on the left hand side we have T. That's okay because T is a disjunctive element. But on the right hand side we have the negation of a disjunction itself. That is not okay. Is that okay? That are we having an understanding of what is well formed and what is not well formed? Okay. All right. So with this new definition of what is well formed and what is not well formed, so the first question is, what about that whole space of all the available well formed formulae? Is that going to be finite this time or is it still infinite? So I want you to think of a slot machine. So when we have P, Q, R, S, T as our variables, okay, I want you to think of a slot machine. So I can try my best to make a slot machine using text over here, okay. So we'll go ahead and say, okay, here is a slot machine. So the slot machine has slots for P, oops, P, Q, R, S, T. These are the 5 slots. So now the question is, what can be inside, these slots over here? So I'll just convert this to a table. I think it's better to convert it into a table. Okay. So a table in Markdown is going to use the vertical bars like so. So excuse my ah where is okay, there we go. I just pressed F1, I think. I just accidentally hit F1 and it popped up the help screen. Why is it not recognizing this is a table? Hmm. I think it's because of the spaces. Okay, let's try get rid of the spaces. Yeah, Markdown is pretty flexible. You can actually make tables, but obviously I'm having a little bit of an issue here. Why is it not recognizing this as a table? Hmm, not liking this. All right, so let's go check it out. So this time we are actually going to website and documentation, which is where we were before. Go to help and then go to using Joplin. And it has a short introduction to Markdown somewhere right here. All right, so Markdown cheat sheet. So headings, easy, PC, not a problem. List, ordered. Code block, unformatted text, not a problem. Tables, okay. Okay, so it wants to use this kind of a table, and I think I'm following the format. Bar, and then the dashes. So maybe it wants to have special spaces between the dash and the bars. No, that is not the case. Hmm. Hmm? No, I don't. I should not be in a box to draw a table. Um, okay, so let's try this one more time. If it doesn't work, then I'll try another way to do it. Yeah, it just won't recognize it as a table. The line with the dashes. Yeah, I have the minimum number of dashes. So you're saying that it might need more. Okay, we can try 2. Oh, it needs one more. Okay, because we have 5 variables. There we go. Yep. It. I forgot. There's one more column. That's why I didn't recognize it. Okay, operator error, Mike. I made a table basically. So, no, I think one would do because what I did not do correctly was I only specified 4 columns instead of 5. Yeah, so this works too. Yep. Yeah. So now I can also just make an empty row like this. Okay, so now we have a slot machine, right? So now the question is, in a disjunction, what are the 3 choices for each one of the 5 variables? How many choices do I have? Well, I think we know that it can be present, right? Just P all by itself, it can be present, it can be absent, P is not there, or it is negated. So we have 3 choices for each one of the variables in a disjunction. Okay, so that means if I just go like, okay, we'll pick this up. Okay, we'll say yes, one of those. Okay, so we'll say yes, and then none of this. Okay, maybe the negation of this, and then maybe none of this, and then one of this. Okay, so this way, I'm basically using a method to encode one of the finite numbers of disjunctions that I can make out of these rules. So in this case, what the resulting expression is P or not R or T. Okay, so let's just kind of pause here and see if you guys can see how P or not R or T is encoded using 1, 0, and -1 in a table like this. 0 means we are not mentioning Q. Q is not a part of this expression or the disjunction. 1 means, yeah, we want P non-negated. And the -1 means, yeah, we want R, but we want it to be negated. Are we okay with that representation? Okay. So now that we understand, this is one way to represent a disjunction that involved, the 5 variables that is in this particular system. So now the question is, do you think there's a finite number of disjunctions that we can come up with using only these 5 variables? The number of variables is finite. It's just 5. Each variable has 3 choices in each disjunction. It can be present, unnegated. It can be present, negated, or it can be absent. 3 choices, right? So what is the total number of disjunctions I can make based on these rules? No. Okay, we know it has to involve 3 and 5 somewhere. Hmm? Okay, so all right. So this is where we have to be careful with the terms. Okay, the term is for P being a 1, Q can be a 1, a 0, or a -1. For each way P and Q can be arranged, R can also be a 1, a 0, or -1. For each way we arrange P, Q, R, S can be a 1, a 0, or a -1. So what is that suggesting? Yep. Unfortunately, I don't have the marker, the dry board marker, to actually do anything on the whiteboard, and I didn't bring my tablet today, but I can still do it using a text representation. So we'll go ahead and take a look at the text representation. Um, okay, we can do it this way. I can only show you like a few of the entries because this is going to be like, or we can simplify the table. Let's only think about 2 variables. Okay, is that okay? To simplify this whole thing to only have 2 variables, just to illustrate how we do the counting. Okay, all right. So we'll simplify this whole thing. Okay, to only have 2 variables, just P and Q. Okay, without the other 3. All right, and we need an empty line and get rid of the extra thing here. Okay, there we go. Are we good? Okay, so I'm going to go with a specific order here. Mm, so this can be, okay, let me -1, 0, and whoops, 1 over here. And we have -1, and I just want everything to be in order. That's all. So get rid of 0, give it a -1. Okay, so are we good so far? When P is negated, Q can also be negated, Q can be absent, or Q can be non-negated. Is that okay? So each row is corresponding to a disjunction involving P and Q. So the first row is basically saying not P or not Q. The second row is saying not P. We don't mention Q whatsoever. The last row means we have not P or Q. Is that okay? All right. So now we say, okay, we have exhausted every way to involve Q when P is negated. So now we just have to be we can do it this way, and then we say, okay, what about not having P at all? Okay, so these three choices, okay, which you cannot see the entire thing. So the next three choices, which are these three, is basically saying, okay, let's not mention P at all. So this row, 0 and the -1, -1, is saying, oh, we just have the negation of Q. The second row is the interesting one because we are not mentioning P or Q. So we'll talk about what that means, okay? Because what that means is, oh, we are just saying true. Excuse me, we're just saying false, okay? We're just saying false on that one. And then the last one is we have Q that is not negated. Is that making any sense so far? Okay. So now we take this and go like, okay, now we have exhausted every single way to have P being negated, P being missing or absent. So the only three things left is for P to be present and not negated. And I need one more. Okay, there we go, like so. All right, so let's take a look at the table. Okay, the last three rows of the table. This one is basically saying we have P or not Q. P by itself, not negated. P or Q. Are we doing okay so far? So how many rows did I end up with? 9 rows. So how do you combine the 3 and the 2 to get to the 9? Exactly. 3 to the power of the number of variables. So with 5, okay, with 5 variables, what would be the number? 3 to the power of 5, which is what? 81 times 3, which is 273. So I'm not going to give you that table. Wait, I can do that pretty easily. I just need to write a quick program, with 5 levels of nested loops. With each level, it goes from -1 to 1. That would be pretty easy. But are we understanding why the total number of well-formed formulae would now be finite? Now, why is that a big deal? We talked about this in the previous class. I just want to see if you guys remember why it is a big deal to have a limited number of well-formed formulae. Your haystack is now a fixed size, okay? Which means you can actually rule out, that the needle is actually in a haystack. You can differentiate between the two cases of I haven't found the needle yet versus the needle is not even in a haystack. And that's a big thing. Are we good so far with this? All right. So why is this related to resolution? What is resolution going to do? What does resolution have to do with this? Well, first of all, what is resolution? Do we remember what is resolution? Let's go back to take a look at resolution. This is resolution, okay? This is what we talked about last time. So why do you think resolution has to do with the new way of representing well-formed formulae? Because this conjunction never has to be explicit. Okay. So if every well-formed formulae is in the form of a disjunction, then we only need one rule, which is the one that we just looked at here. This is the only one rule that we need. And then we can just go like, okay, so we are just looking at two expressions. If they, um, let me see what I mean by that. So if they are related, meaning that one has the negative version of something, the other one has the non-negative version of exactly the same thing, then we can say that, oh, if these two are true, then we also know this has to be true too. Yep, yep. This is the resolution rule, but encoded um, as a production in zeta. All right. All right, so let's give it a try. Okay, so we are going to give resolution a try and go like, okay, what do we mean? What do you mean by that? So we'll go ahead and switch back to Joplin, and I'm going to go here. Okay, because this is just a quicker way for me to type Boolean expressions. So we are going to start with, okay, we'll start with something that's simple, okay? So we'll have P or not Q as a expression. We'll have Q or S as an expression, and then we'll see what we can do with this, okay? But we can throw in something that that cannot be simplified in any way. We'll just throw that in, okay? So with this, okay, first of all, do you think this is a legitimate CNF, conjunctive normal form? It is a conjunction where each thing you are ending is a disjunction, and then inside each disjunction, we can only have a variable or the negation of a variable. Does it meet all of those requirements? Okay, you turn your head. This is one single conjunction. It has three components. Each component of the conjunction is a disjunction, and then within each disjunction, it is only involving either a variable or the negation of a variable. Yes. No, we're trying to apply resolution. Okay. So the question is, can I apply resolution in this conjunction? So we'll go ahead and take a look at resolution on one side and then look at the formula on the other side. Okay, so is that better? Yep. We don't have what? A negation? Well, but we do have, okay, think of it this way. Think of it as P is phi, psi is not Q, psi is Q, not, okay, excuse me, psi is Q, and then rho is S. Would that work? Would that substitution work with only the first two of the three disjunctions? Okay, let me say that one more time. Okay, so we'll go ahead and do the substitution here. So substitution, substitution, substitution. Okay, there we go. So the substitution is going to be, we want to replace phi with p. Okay, so you guys can focus on this side. It's a whole lot easier to read. So we are replacing phi with p, and then we are replacing psi with q, because that's the one that is negated on one side but not negated on the other side. Um, Actually, I take it back because we have to use S over here. There we go. All right, so one more substitution. So the last substitution is going to be rho. So now we look at rho and we say, okay, let's replace rho with P. Okay, now I think that will work. All right, so let's check. Okay, is it going to work? So I'm saying that This phi here is replaced with the s. This psi here is replaced by q, which is not negated when it's next to the s, and it is negated when it's next to the p. And then finally, I'm also replacing rho with a p. This is rho, which is next to the negated psi, but because psi itself is q, on over here it is next to the not q. So does the pattern match with the substitution that I'm talking about? Okay. So this is important. Okay. So I want to give you guys more time to think about this, to understand, whether the substitution that we are talking about here is going to make the first two of the conjunction, the first two disjunction of the conjunction to match this particular pattern here so that I can determine whether resolution can be applied. So are we convinced that we can apply resolution? Okay. You can see some of you are still not convinced. So I need to know why you're not convinced. Yes. Plus is a or. Yep. The plus is a or, and we talked about that notation from on the first day of the semester. That was also the first day when I said you might want to put all the notations on a little piece of paper at a corner because we are gonna use it. It's just a whole lot easier for me to type. That's why I use that notation. Yep, yep. All right, cool. But are we still working on the substitution to see whether the substitution will make this pattern fit the first two of the expression? So if you're not convinced, okay, that's because the ordering is a little bit off. So let me go fix the ordering so you can see a little bit better. Um, right. So the to fix the ordering, I'm gonna have to put it like this: S plus Q on one side, and then we have not Q or P, which is not the way I like it because it's not alphabetical. But when you look at the ordering, now it is a lot more clear that this S over here is the same as this phi over here. This Q over here is the psi over here. The not Q is the not psi, and then the rho is just the P. Is that working out? Okay. Are we all good? All right. So what does that mean then? Well, that means this whole thing, this part, only this part here is the same thing can imply um, whatever phi is s, or rho is p. So what does that mean? In other words, I can now say s or q and not q or p is implying um, s or p. Okay, that's the result of the implication. So what does that mean? If the original expression is this, okay, so now the question is, can I just simply append the result of the implication at the end of this? And if this is true, I'm also guaranteed that this is true too. Let me say that one more time. If I tell you ahead of time that this thing here, um, mm, let's see, why is it in? Oh, I think it's because of this syntax highlighting. So if I tell you ahead of time that this is known to be true, don't ask me why. Okay, we have some additional steps to prove that this is true. So if that is true, and the first two item of the conjunction implies this, can I also make a conclusion that I can just attach whatever is implied, and this whole thing is also guaranteed to be true? Yes or no? Yes. Okay. So how can you convince yourself of this? Okay, it might make sense in your head, right? So how can we convince ourselves, that absolutely this is true? Yep. But how do we prove it? But the problem of the proof on this side is we only know this implication is true, right? But this implication being true is really important because if this part is true, what is it telling you? All components of the conjunction has to be true, right? So if all the components are true, that means the first two components are also true. If the first two components are true, and we know this implication is true because of the proof that we have here, so that means S or P is also guaranteed to be true. In other words, I'm just extending a bunch of stuff that is already true with another expression that is also known to be true, that is derived to be true. So that doesn't really change the truthfulness of the final conjunction. So what this means is I can apply resolution. Whatever I come out of using resolution, the result of the resolution, I can just append it at the end of the conjunction that is already long, just to make it longer and longer and longer. Is that okay? No? Yes? Mm-hmm. Wait, wait, wait. No, no, this part really just literally. Okay, let me go back to the first one. Hmm? Well, each piece is true. Okay, so in this case, if I tell you this part is true, I'm telling you that between S and Q, one of them has to be true. At least one has to be true. And then between not Q or P, I know at least one side has to be true, but we don't know which side or whether they can both be true. And then between S and T, we also know that at least one side is true, but we don't know which one. Is that making any sense? So you cannot make a conclusion on the individual variable, but you can only look at the entire disjunction and say, yeah, we know this disjunction is true, but we cannot infer which part of the disjunction is true. Yep. All right. So this is one example. Okay. So now the question is, what if we have a really tricky situation like the following? So this is a little tricky, because it has P and then we have not P. Okay. And I claim that this can also be, I can also apply resolution here. And you guys look at this and go like, no, there's no way we can apply resolution because the P is not even a disjunction and not P is also not a disjunction, not a yeah. So it doesn't fit this particular pattern. So as a result, we cannot possibly apply resolution here. What if I were to kind of mess this up a little bit like this? Okay. What what if I were to say, yeah, let's do a false or, and then this is or false. Would that change the meaning of P if I just say false or P? That would not change anything because false is the identity of disjunction, just like zero is the identity of addition. Does that make any sense? Okay. So that means, oh, look at this. It does match the pattern. Okay. So in this case, what is the substitution that I need in order to say, yeah, let's apply resolution? It does work. Okay. So the substitution is going to look like this. Okay. We want phi to be replaced by false. Nobody says I cannot replace, a Greek letter with a constant, right? Constants are allowed. And then we are going to replace P, or not P, but psi with P. And then we are also going to replace rho with false again. So don't you think that this particular way of doing substitution will make this conjunction match the resolution rule? Is that okay? So what can we now conclude? So now we can say, oh, okay, so we can apply resolution, but that means this implies false. Well, okay, technically it is false or false, which is false, okay? Is that okay? Because according to the resolution rule, we pick the thing that is not making the connection between the two disjunctions, and then we just concatenate all of the other stuff. So in this case, the connector is P and not P, so we take that out, and then everything else just got concatenated. So we have the false, false to be concatenated together. Does it make sense? Okay, we just applied resolution again. So according to the rule of resolution, each side of the of the implication may or may not be true. What we know to be true for sure is the implication itself, right? Yes. So that means, oh, okay, we know the implication is true. We already know one side is false, okay, because false or false has to be false. It has no choice. So what does that mean? What does it mean? What does it mean about the left-hand side? It also has to be false. Let me say that one more time. Okay, in this time I'm going to use a truth table to work on this. So what we are really saying is we have x, we have y, and then we have x implies y. X implies, which is right arrow, and we have the y over here, and then we turn it into a table. Okay, dash, dash, dash. There we go. All right. So now we have the truth table. Okay, 0, 0, true. 0, 1, true, 1, 0, false. That's the only time we have a false. And then we have 1, 1, 1 over here. So on this side, we have the truth table of implication, which was also something that we introduced on day 1 of this class. So when you look at this and you go like, okay, we know this implication. This implication here is true. Why do we know? Because of that crazy proof that I did the other day. This implication is guaranteed to be true. All right. So now we switch back to the truth table and go like, okay, we are looking at this row, or this row over here. But when you look at this over here, we also know the right hand side has to be false. So now we apply the filter, okay? Because we know we're looking at one of these 3 rows, but only one of these 3 rows correspond to the right-hand side also being false, which is this one here. So by that, we also now basically are saying, oh, so that means X also has to be false. Is that okay? So we come to a conclusion that's really obvious because P and not P has to be false. But we did not prove it in the more conventional way of saying, okay, between P and not P, one of them has to be false, and therefore the conjunction between those two has to be false. We are using resolution to prove that P or not P is false. Is that okay so far? Okay. So now the question is, why are we so obsessed with something being false? I thought we are trying to prove something being true. So why are we suddenly switching and turning 180 degrees and now we are focusing on false? So this is the last piece of the 3 components for this whole thing to work. Okay, it is called proof by contradiction. Okay, so, but I'm not going to focus on proof by contradiction today. You can read about it and then we'll talk about it on Monday because I need to talk about the homework assignment. So, proof by contradiction is down here somewhere, right there. Proof by contradiction has its own proof. In other words, I can prove that proof by contradiction works. But we'll talk about that on Monday. So, what we'll do today, right now, is to focus on the homework assignment. So the homework assignment is saying, okay, we need to be able to convert every Boolean expression to a CNF in order for resolution to work. Okay, so now the question is, this is your assignment, which is not what I'm going to use as an example. Okay, so this is your homework, but the actual example that is in the notes here is up here. So I give you this particular, expression with all the parentheses and whatnot, and I want to convert it into a CNF. This is, by the way, the scenic route to do it. I found a shorter way to do it. So let me share the shorter way to do it first. So the shorter way to do it is basically one of the first items, that I have talked about here. This is the easier way to do it. All right, so we are going to look at each one and figure out, okay, what route did I use to move on to the next row? Okay, so I'm going to use the traditional, commenting syntax here. So what did I do in order to go from the first row to the second row? What is the difference? So we took the implication that is here. Okay, so we took the implication and then we converted the implication to the negation of the left-hand side or the right-hand side not negated. Uh, when did we talk about that? You guys won't like the answer. The first day of the semester. Yep, we did talk about it. Okay, even though we did not apply or use it very often, this is when it is useful. So now we go like, okay, so I'm going to, kind of really spell out the rules. Okay, so we say A implies B is the same thing as not A or B. Okay, so we can focus on the whole thing here. All right. So now between the second and the third row, what did I do to get the result? It is De Morgan's law. Okay, it's called De Morgan's law. So what De Morgan's law is doing in this particular case is the negation of A or B is the same thing as not A and not B. Is that okay? All right. Have we talked about De Morgan's law in this class? Okay. All right. So now what about here? What about from the third row to the fourth row? What got changed? I think that's the only change is double negation goes away. Okay, so we are basically saying double negation of A is just A itself. Okay, are we convinced about this particular rule? We are. So what if I'm not convinced? What am I going to do? Uh, no, a truth table. You just use a truth table to prove that the negation of a Boolean variable is really just the Boolean variable itself. A truth table is all you need. All right. So what about this one here? So how did I go from here to here? It's called distribution. Okay. So this distribution looks really awkward, for people who only know, arithmetic algebra, because this distribution looks like this in the abstract form. A plus B and C, or A or B and C, is the same thing as A or B and A or C. That's the one distribution that works in Boolean algebra that is not in the common algebra. Okay, so you guys look at this and go like, "Oh, really? I'm not convinced." What are we gonna do if you're not convinced? A truth table, exactly. Do you guys want me to do a truth table on this one? Let's do it. Because I can see that you guys look at this and go like, "That's dubious." Really? Okay, well, we'll do a truth table. It's not that hard. Okay, so I'm going to put it over here. So we got A, B, C as independent variables, and then we have the expression of A or B and C by itself, and then we have the other expression that we think is the same, which is A or B and A or C. So those are the 5 columns that we have, and then A, B, C are um, independent variables. So when they are all, okay, let me just make it into a table first. And why is it not turning into a table? Did I miss something again? No, I did not. Mm, okay, A, B, C, A or B, C. A or B and A or C, that should turn it into a table. Oh, right. Yep, you're right. Okay, I forgot about the dash. There you go. Thank you. All right. So now we have to fill in this space. From your perspective, we have to fill in this space here. What do you think is the answer? A, B, C are all false. So what about A or B and C? Yep, that's a false. And what about this one? A, B, C are all false. A or B is going to be false. A or C has to be false. False or false is also a false. Okay, that's the easy one. Okay, now we have 0, 0, 1. Okay, so we'll go back to take a look at this one. I think it is still false because B is false. So that means B and C is going to be false. A is still false. So A false or false is going to be false. Huh? It's B. It's literally B conjunction C or B and C. If it looks like multiplication, it is a conjunction. Yep. All right. What about the other one? What about this one over here? A is false. B is also false. A or B is false. If one side of a conjunction is false, the whole thing is going to be false. Is that okay? Are you guys starting to get used to the notation? What looks like a multiplication is conjunction, and the so-called addition is really a disjunction. Are we still doing okay? All right. All right. So we will take a look at the next one, which is false, true, false. So we'll go ahead and fill in the table. Okay. So what about this one? B is the only thing that is true. If B is the only thing that is true, this is still going to be false. Okay. And if B is the only thing that is true, A or C is guaranteed to be false. So the whole thing is still false on that side too. So you can see how, I'm just filling in this whole table step by step. So now we have both B and C being true. If B and C are both being true, then B and C is true. And if we have at least one side of a disjunction being true, the whole thing is going to be true. And on this side, we have B being true, which means A or B is true. We also have C being true, which means A or C is also going to be true. So now we have true, and it is a true. Are we good so far? Do you guys want me to finish the whole thing, or do you think you're convinced? Okay. So if you're still not convinced, I will leave it to you and use your own time to kind of finish up the additional 4 rows. So basically, what we have done is to prove that this expression as a Boolean expression is really equivalent to this expression over here. It is distribution, but it's not the way you use it in normal algebra. But it does work in Boolean algebra. So getting back to the derivation, this is the rule that we use from here to here. All right. So now we are taking a look at what about from here to here? What rule did we use? We noticed that we have not P or P over here, so that becomes true. True or whatever is true. So that's why I basically collapsed this whole thing into just true. So there's one step in between that I did not um, list. So the one step in between that I did not list is basically just this one because because not P or P, just this sub expression here, that is guaranteed to be true. Are you convinced? Okay, because between P and not P, one of them has to be true, the other one has to be false. But because these two are in a disjunction, the disjunction itself has to be true because one side of these two has to be true. Are we convinced? All right. So now, so I'm going to kind of state the rule that we use here. So basically, the rule that we use here is A or not A is guaranteed to be true. So now, what about from here to the one below? In other words, how did we ditch the or t over here? So that is a simplification of anything or true is just going to be true. Are we convinced? Okay, because in a disjunction, if at least one side is true, the whole thing is true. So what if I tell you one side is always true? Then the disjunction is always true. Is that okay? All right. So now we move on to this one over here, okay, which is basically how did we ditch the and true? So this one is basically saying anything and true is just that anything itself. Are you convinced? Are you convinced that A and true is just A? True is the identity of conjunction. Are we okay with this one? All right. So if you're not convinced with any one of these derivation, you can always use a truth table to prove it. Okay, because these are axioms, and axioms in Boolean algebra they're always provable using a truth table, which is the beauty of Boolean algebra is, oh, okay, it's not just abstract, you can actually make it concrete. All right, so how did we go from here to the last one? This is distribution again, okay? So this is basically the same distribution that we saw earlier, which is A or B and C. It's the same thing as A or B and A or C. So the only question is, which between A, B, and C, which one is the not P, which one is the R, and which one is the not Q? In this case, the ordering is exactly the same. So A, which is a placeholder, is the not P. B as a placeholder is R, and then C as a placeholder is not Q. So that's how we can apply the distribution to get to the last one. And is this CNF? In other words, if you look at the last row, okay, let me use a mouse pointer to point to it. So if you look at the last row, does it meet all the requirements? The overall operation is a conjunction. It's a conjunction of stuff, okay? Each item in the conjunction is in a disjunction. That looks like a disjunction. That looks like a disjunction. For each disjunction, each item in the disjunction can only be a variable or the negation of a variable. Does it also meet that rule? That's a negation of a variable. That's a variable. Also the negation of a variable. This is also the negation of a variable. So it satisfies all the rules. So now we have a CNF or a conjunctive normal form. Are we good so far with this discussion? So what if I were to tell you, you can give me any random but valid Boolean expression, and I can always turn it into a CNF? Are you guys convinced that we can do that? Okay, so there's actually a proof to show that yes, we can always do that. But the question is, how do we go about doing that? So this is a good time for you guys to test me because after the exam, I'm sure most of you are going like, okay, I wish I could turn the table and test and have tech to take the test instead. So this is your opportunity to do so. Give me a random Boolean expression and I'll show you how to turn it into a CNF. So you guys can, it's a little bit harder for you to describe it, okay, because you're trying to describe things in parentheses or not and whatnot. So if you have an idea of what you want me to work on, you can put it on the piece of paper, and then I will just put it on the board here. The alternative, the alternative is for me to teach you guys how to randomly generate a Boolean expression, so that you can also use that technique to test yourself. It has to be well formed. Okay, so it looks like, maybe it's a good idea to teach you guys how to generate a random Boolean expression. Yes? No? Maybe? Okay. All right. So the way we generate a random Boolean expression is to look at it this way. So this is the way I look at it. Um, you have to look at all the operators that take two operands, okay? There are only three of them. So we only have or, we have and then we also have implication. So those are the three operators that will take two operands. We have one that takes only one single operand, which is just negation. And then we have the variables. We have P, Q, R, S, T. Okay. So depending on how complex you want the whole thing to be, what you want to do is to say, okay, pick one of those three operators that take two operands. So go pick one. Hmm? Implication. Okay, so I'm gonna use an equation to do this. Okay, so we're going to pick an implication. So which is a oops. Uh, ah. So implication is right arrow. So we now have to figure out something on the right hand side and something to the left hand something to the left hand side and something to the right hand side. So let's just say that you guys don't want to make it easy on me and you want to pick something that is also a binary operator as the left hand side. So between these three, pick one. And okay, so we'll do a wedge over here. What about the right hand side? Pick another Boolean, pick another binary operator, meaning it has two operands. Between these three, pick one. Hmm? Another implication? Okay, we can do that. Okay, so, but you can see how I'm constructing the overall expression structurally, right? So if you want to, okay, we can keep going, okay, using binary operators and whatnot. But you can always say, okay, I think we got it complex enough that we can just go for single negations. Okay, so do you want to put a negation somewhere within these parentheses? Hmm? The first one? Okay, so we'll pick a negation on the first one. Okay, so now we have a negation of something. So you can see that I'm still using a lot of empty parentheses because each empty parentheses can be a full up expression. In other words, I am creating the overall Boolean expression recursively, starting from the top, and I just look at each branch and go like, oh, okay, with each branch, I can make it complex and whatnot. So let's just say that, okay, let's just say that we think this is complex enough already. So now each one of the parentheses can only be a variable. Or if you guys think, oh, I want tech to work on something, an Boolean operator that is negated. Okay, so let's pick one. So let's pick one of these three to be inside this particular negation here. Pick one. Conjunction or disjunction? Hmm? Disjunction? Okay, so we'll pick a disjunction. All right, there we go. So I think we have enough stuff here that we can now start to specify individual variables. Okay, so what do you want to put here on this between these two parentheses? Okay, just P. Okay. What about the next one? R. Okay. And what about here? Okay. And over here, T back to P. Okay. All right. So this is what we'll work on. But do you see the process of creating a quote unquote randomly generated Boolean expression? Yes? Okay. So this is something that you can work on with each other. Okay. So let's just say that you guys are studying together and you want to practice how to convert an expression into a CNF. So one person can go like, okay, I'm just gonna, you know, randomly generate an expression, and then the other person will go like, okay, I will try to turn it into a CNF. All right. So now we will work on this. Okay. So first thing is to remove the to rewrite this in the more um, the easier format. So we are going to say this is a negation of P or R, and then that whole thing is going to be ended with the S, and then we take this entire thing that is implying T implies P. So I'm just removing the unnecessary parentheses just so that the whole thing is easier to read. Are we good so far? Okay. So the way I do this is I always remove the implication first. So we have two implications, and we'll do it one step at a time. So to do it one step at a time is, I'd like to work from the inside out. So I would convert this one to this one first. So that's how I do this one. Okay, and now I can work on the one that is on the outside, which is really just negating the left-hand side, turning the implication to an or, and make sure that we have parentheses, in the correct places. That's all we need to do. Are we good so far? All right. So now we have a or in between, and then we have, basically this is also or. So technically speaking, we don't need the parentheses anymore because of the associative law, so we don't need those extra parentheses. All right, so now we have the negation on the outside, and we also have a negation on the outside. We'll go ahead and do the De Morgan's law from the inside out. So De Morgan's law is basically saying, recognizing that we have a negation of an or, so that means we turn it into an and where the components are both negated individually. All right, so we'll take this, and then we say, okay, get rid of that, and it becomes that. Okay. And because they're both, okay, let me just put the extra parentheses on just to emphasize, okay? So with this one, we started off with the negation of P or R, and then by applying De Morgan's law, it becomes not P and not R. Is that okay? All right. But then we have a bunch of ands, okay? Because when you look at this part is an and then it's also ended with something else. So that means that the parentheses are not needed. It's always, to me at least, it is always good to remove extra parentheses, just so that we don't impose extra structure that are not needed. Okay. So now we look at this and go like, ugh, do I? Where? Where do I need the extra parentheses? This one? Nope. We have one open, one closed, so they're matched. All right. I think you guys have accidentally given me a easy one to work on. Because right now the only thing I can really do is De Morgan's law again. Because we have a negation of an and, so that has to be done. In other words, the negation of an or versus a negation of an and, you have to apply De Morgan's law. Those are mandatory. Okay. Anytime you can see that there's a chance to apply De Morgan's law, you have to do it. So that means we can just go ahead and do this. Okay. So we take this knot and then we put that knot, we distribute the knot into the individual components, and then we just use a or to replace the and. Turning the whole thing into a CNF. All right. So double negation goes away, and I think I did one too many. There we go. Okay, that one stays. So now we look at this and go like, okay, what else can we do here? Well, the whole thing is a gigantic OR, which means that the parentheses are not really needed. So we use the associative law to remove the parentheses, like so. And then we can now say, oh, we have two, p's, p is appearing twice, and they're both not negated. So that means we can get rid of one of them, and it doesn't change the meaning of the whole thing. And I think we're done. This is a CNF. You guys look at this and go like, no, it is not a CNF. I don't see a conjunction. Fine. If you want to see a conjunction, is that a conjunction now? You go like, but wait, Tech, I don't like this. This is not a disjunction. It's supposed to be a conjunction of disjunctions. Happier now? So now it really is a CNF, right? It is a conjunction of disjunctions, and in each disjunction, it is only involving constants or variables or the negation of variables. So that turns out to be an easy one. Now, okay, I know you guys are eager to get out of here. So now the question is, did Tech make any mistake in between? I don't know. I could have. Okay. So how can you prove to yourselves that I did not did or did not make a mistake. You make a truth table. You make a gigantic truth table that has five variables, P, Q, R, S, T. Okay, so it's kind of big with 32 items. Okay, on each row, you compute the value of the original expression, and then you also compute the value of the expression that we end up with, and make sure that those two are the same on every single row. Yes. Hmm? There can be multiple expressions. Yeah. So it depends. The homework assignment only needs to end up with a CNF. It doesn't ask for the most optimal CNF. So you can end up with a CNF that is not optimal, and I'll still count it as 100%. Yeah. Yeah. Okay. But getting back to the verification of all of these steps. So are you going to do everything by hand, or what are you going to do to verify that the two expressions are in fact equivalent to each other? What are you going to do? If I'm telling you this is what I want you to do, how are you going to do it? Well, you have a few things you can do. You can put this into ChatGPT or Gemini and ask you whether this expression is the same as this one. That's one way to do it. Hmm? I don't know how much you can trust ChatGPT to derive this sort of thing. So what is the other way? What is the other way? What is the most basic way that you can do this? Remember, CISP 360 is a prerequisite of this class. Exactly. Write a program to do this, okay? And how complex is that program? How many lines do you think that program is going to have? I can do the counting on one hand. It's going to be a 5 level loop because one level for each Boolean variable. So it's going to be 5 plus 5 because we like to have the open brace and the end brace on a different line. At the deepest level of the nesting, you are going to type this out as a Boolean expression, and then you're going to type this out as a Boolean expression and see if they are the same. If they are not the same, you can just do a C out that has in double quotes, you say tag screwed up, and that's it. Return 0 right away because that's all you need is to find that there's one row that is not the same. Okay, so if they're the same, you just keep rolling the loop until you get to the end, and then at the end of everything, right before return 0 in your main, you just say C out, and then you say tag was right. That's the program. It's going to be about, I'm going to say 20 to 25 lines long. The most complicated part is C++ does not have implication. So that's the only part that gets a little bit dicey, but you can always implement your own function that says implies, right? So you make your own function that returns a bool that is implies. It takes two bool as parameters. It is simply return the negation of the first parameter or the second parameter. There you go. There you have your implication. Is that okay? So how long do you think it will take you to write that program and then come up with either the conclusion that tech screwed up or tech was right? Hmm? A few minutes is about right. Okay, maybe half an hour. Okay, give it about half an hour because it really is just five loops. It's 5 levels nested. For p equals 0, p is less than 2 plus p. That's 1. And then the second one is for Q, R, S, T. They're all nested like that. And then at the deepest nesting level, then you compute the both of those expressions and see if they're both true at the same time or both false at the same time. If they're not both true, or both false, then we have a problem. You just do a cout, text screwed up, return 0, done. All right. So I would say give it a try because until you give it a try, you won't realize how simple that program is. And you're going to be able to use this approach as you do your homework to make sure that all the steps, you only have to spot check, right? So every 5 steps, you just do a spot check, make sure that they're all equivalent. So this will help with your homework as well. Are we good? All right. Okay, so we are done with today's lecture. You do have your homework that is due in a week. I do recommend you guys to get started as early as possible so that if you run into any problem, we can use next Monday to talk about it at least a little bit. All right, have a nice weekend and try that program because I think you guys will be impressed by how quickly you can write that program.